Hi, everybody. Thanks so much for joining us today. I'm so excited for this topic. Actually, everybody on the OSA COM organizing community is really excited for this topic. I'd like to introduce Jan from Dashbook, who's going to be talking to us about an on-the-fly method for doing materialized views with Apache Iceberg. Thanks so much, Jan. Take it away.
Yes, also thank you from my side for joining me here today and also giving me this opportunity to talk to you. And yes, as you mentioned, my name is Jan Kaul, and I'm really excited to share with you today how I think Iceberg Materialized Views can revolutionize the way we do data transformations in the future. With Iceberg Materialized Views, you can declaratively express how you want to transform the data independent from the underlying data platform. As a result, we get data pipelines that are composable by design, even if we use different query engines or data warehouses. But before we get to that, let's have a quick look at the different stages data is typically going through from its raw form until it can be served as useful asset. So here I've depicted the typical data life cycle from the data sources on the left side until the data consumers on the right side. During that process, data goes through different stages. The first step is where data is loaded from external systems into a browser or also staging layer. Here, typically, or nowadays, typically the data is just replicated into the browse layer without transforming the data, or maybe just small transformations are being done here. The next step is then to clean and structure the data to make it ready for any further analysis. This data is then stored in the silver layer here in the middle. And as a last step, I can the names are actually not really represented here. And as a last step, the data is then from this clean form transformed into business metrics or some data sets which can answer business questions. And these data sets are typically served to business intelligence and machine learning. First, I want to dig into the first step where we extract and load the data from the source systems. The problem here is that nowadays a normal company typically has a lot of different data sources where the data is coming from. It might store some data in transactional database systems or event streaming platforms, or it might also get some data from external APIs. These are typically all loaded into some analytical OLAP database so that it's much easier to transform it and have a better overview of it. And this is a very complex question, and there's typically different providers which solve this problem. But the complexity gets even bigger if this problem has to be done for also various different data warehouses. The problem would be much simpler if we had one single data format where we could load the data into and which can then be accessed from different data systems. This is where Apache Iceberg tables come into play. Apache Iceberg is an open table format for large analytical data sets. One great benefit of it is that it's an interoperable data format, which can be accessed from a lot of different query engines and data warehouses, like Spark, Trino, Snowflake, Athena, only to name a few. And more systems are developing support for Iceberg on a daily basis. If we have one system to load the data into, we don't have to make a difference between all these different warehouses, and we can just access the data from this one single source of truth. This is also handy if you want to use different systems, for example, on this data, if you want to do some business intelligence in Snowflake, or if you want to do some machine learning analysis in a Python notebook. As most of these systems nowadays support Iceberg, Iceberg is the perfect candidate for this format. Let's have a look at how Iceberg is structured underneath. Iceberg is actually a metadata layer on top of the actual data files that lie in storage. And this structure provides a couple of interesting benefits. For example, it lets you create snapshots of your data. If we look at the graph here, we can see an S0 snapshot, which tracks certain data files. All the files being tracked can be seen here in yellow. And we can see that it's not, that not all data files are covered. If now new data is inserted into the table, a new snapshot is created, which is depicted here as this S1 snapshot and drawn in blue. These snapshot capability also enable us to do time travel, where we can access the S0 snapshots, for example, later on, seeing the state of the table at a certain point in time. And additionally, it also lets us do incremental changes to see only the data that has been changed since the last time we looked at the table at a certain snapshot. All these capabilities are really great if you're doing a data platform, because it also enables incremental computation. Moreover, Iceberg also supports hidden partitioning, where the data files are partitioned by a certain logic, which increases the query performance a lot for certain types. And additionally, Iceberg also supports branching, where different snapshots can belong to different table branches. For example, here, the S0 snapshot could belong to a main branch, and the S1 snapshot could belong to some development branch. Then we could have a look at the data in the development branch and check it for correctness. And only after we've checked for correctness, we could merge the development branch into the main branch, making sure that all the data on the main branch is correct. So hopefully I've convinced you that storing the data in Iceberg tables gives a lot of benefits. One main one is interoperability and all these nice features on top of it. In the next step, or do you have any question? Does anyone have any questions regarding Iceberg tables before I jump into the next section?
Don't see any questions yet.
Okay. So as a next step, I would like to look at the transformation stage. And to highlight one key characteristic of analytical data transformations, I like to contrast them to typical operation on transactional databases. For transactional systems, the data sources have typically one characteristic, which is that the data is generated in the process of inserting the data. There's never a prior record anywhere else in the data. This can be seen in everyday scenarios, for example, when a user signs on a website or creates an order in an online store. The data is created in process and inserted into the database without it being stored anywhere else. This is different for analytical system, where the data is always derived from existing data. This data typically originates in some external system, like a transactional database or event streaming platform. And it never happens that you're just inserting any new data in an analytical table without it being recorded in the actual source system. Again, so the key highlight here is that for analytics, the data is always derived from existing data. This is the main reason why we see many companies using views for the transformation logic. With this approach, you first also load the data from the external systems into the staging layer, here seen as the orders and customers table. And any further transformations are expressed in terms of views, referencing the tables from the staging layer. The fact that the analytical data is always derived from existing data makes views a perfect fit for that. With views, you can declaratively define how you would like to transform the data without needing to worry about data freshness, tracking changes, or the idempotency of operations. If you were using tables, you would need to track what data you've already processed and make sure that you're not duplicating any data if you've ever rerun a pipeline or something. So if using views is so perfect for data transformations, we're finished, right? Well, not so fast, because actually using views for transformation can be not so fast. One issue with views is that they're always executing the entire query, even if the underlying data hasn't changed. And for typical data platforms, the amount of data that is regularly updated or inserted is quite small compared to the data that stays unchanged. So if you're using views, you're rerunning computation that has been run before, because most of the data didn't change from the last time you've executed the view query. This means you typically need a much larger data warehouse to handle all this computation than you would if you were doing like incremental computation. So this is where materialized views come into play. They combine the simplicity of views with the performance of tables. Just like a regular view, materialized views are defined by using a query that is executed. But unlike regular views, the query is pre-computed at an earlier time and the results are stored in an external table. When the materialized view is queried, this pre-computed data is then returned to the user without needing to rerun the query. This saves a lot of computation time. An additional feature which can be possible with materialized views are incremental refreshes, where only newly updated data or only the part of the query that references only new data is rerun to update the data in the storage table. If we look at the industry, we see a lot of materialized view-like products being introduced, like Delta Live tables from Databricks, reflections from Dremio, or dynamic tables from Snowflake. The problem is that every vendor has their own product, and it cannot be used with other query engines. Just like Iceberg tables provide a vendor-neutral standard for storing your data, I would like to see a future where Iceberg Materialized Views provide us this standard for data transformations. With Iceberg Materialized Views, you can define your business metrics once, and you can use any query engine to actually execute the transformations. This means you're not longer tied to any specific vendor, giving you the free choice to use the best tool for the job. Additionally, a standard for materialized views would also allow a multi-engine data stack, where you can use different query engines for different pipelines. You can, for example, use a single node query engine like DuckDB or Data Fusion to run on a small data set, and use a distributed query engine for large data sets. Are there any questions at this point? All right, then I'll continue. So now, hopefully I've also convinced you that these Iceberg primitives, Iceberg tables, and Iceberg materialized views provide great building blocks for building a data platform. But now I would like to focus, if we were using these building blocks, now I would like to focus on how the development process could look like. As we see with other tools like DBT, is that a declarative environment provides the best user experience for the users. I'd like to call this pipeline as code, where you as a user, you define the queries in some SQL files or model files and just run a build tool, which will then create the according entities in your data platform for you. Ideally, you also don't have to worry about how these transformations are materialized and also how incremental changes are being tracked. These are currently some issues that you have with DBT, as you have to define the materialization if you want to materialize them as tables or views or as incremental. And if you're doing it incrementally, you also have to specify how you would like to track these incremental changes. This is the problem that Dashtool tries to solve. Dashtool tries to leverage Iceberg Materialized Views with these snapshotting features, which makes it easy to determine which data has been processed and which data hasn't. Additionally, Dashtool also provides SQL analysis, which lets you check for correctness of your SQL queries at build time and not later on when the SQL queries are executed in the data warehouse. Let's contrast the workflow with DBT by looking at this graph here. DBT typically constructs a DAG by analyzing model files and then communicates with the data warehouse to create the according tables and views. Dashtool tries a different approach, where it runs the SQL files to construct the DAG and then constructs the according Iceberg Materialized Views in object storage. Since we have a standard for these Iceberg Materialized Views, there can be different data warehouses which can then execute the transformations defined in the materialized views, making it composable. And as I already mentioned before, you can use different query engines for different tasks. Additionally, Dashtool directly integrates with Git version control. Since Iceberg tables support branching, Dashtool mirrors the definition files of your transformations to the Iceberg table branches. So if you have, for example, a main branch with certain transformations, and you would like to add another transformation in a development branch, you can just create a SQL file with the containing query, add this to the development branch in your Git repository. And if you run Dashtool, it will create the encoding development environment in object storage. So the newly created materialized views will only have data on its development branch, and the main branch won't be affected. This way, Dashtool nicely integrates with your development workflow, where typically Git version control is being used. On top of that, Dashtool also integrates or supports ingestion. Therefore, it integrates with Airbyte sources. Different from Airbyte, the state is being stored with the Iceberg tables, which means that no external state management is required. And as a consequence, you can just run simple Docker containers or stateless Docker containers, which can perform the extraction process for you, which simplifies the setup immensely if you don't have to keep an Airbyte cluster running. Additionally, Dashtool uses Argo Workflow as its orchestration tool. Argo Workflow has many benefits because it integrates really nicely with Kubernetes, which is just like a one-line installation process. And on top of that, you can easily handle the various credentials that you need for different servers by just using Kubernetes secrets, just like you would use for any other backend technology. Are there any questions now?
Yeah.
Otherwise, I would start with a demo. So as I said before,
One question, is there an SDF integration?
No.
No. Okay.
Like SDF is actually has a similar approach to it. And I haven't looked into like if you can make an SDF integration. SDF uses Apache Data Fusion or the SQL parser and analyzer of Apache Data Fusion to construct its DAG or also check for correctness. And also Dashtool uses Apache Data Fusion to check for correctness. Currently SDF, like it supports also SQL transpilation, like to convert between the different SQL dialects, which Dashtool currently doesn't support. So, but that's going to be added in the future.
Cool.
Right. So let's, as I said, Dashtool tries to simplify the development process, and let's have a look at how this development process actually looks like. So as I said, we use this declarative environment where we would like to just write SQL queries or some other declarative format to define how we would like to transform the data. And as a setup, we kind of have to first specify certain connection parameters for Dashtool in general, which is what the dashtool.json configuration file is for. And here you can, for example, insert certain object store parameters which you need to store the data. And then as a next step, I mentioned before that Dashtool integrates with Airbyte sources. And these sources are defined with an name.ingest.json file. And the according tables are created according to the path of these files. So here we are creating a file under the browser/default directory, which will also mean that our table will later be accessible under the browse catalog in the default namespace. And in the configuration file, we provide parameters that the Airbyte source needs to load the data or to extract the data and then load it into the Iceberg table. The format of this configuration file is that first we have an image entry, which specifies which Docker image we would like to run. In this example, I'm just using the source fake, the Airbyte source faker, which is a fake source which just generates some test data. And I've used that so that it's easy for you to just rerun this demo. You can also run this with like a source for Postgres, but then you would also need to run an additional service for Postgres where you extract the data from. I wanted to keep it simple. That's why I'm using the faker source here. And next, Airbyte sources and destinations also provide or require certain parameters. And under the source field, we provide the parameters for the faker source, which actually is not a lot. We just have to specify the number of records we want to create. The destination field contains parameters for our Iceberg destination. These can be found in the documentation and also include certain parameters we have to use for our object storage, like our S3 bucket we want to use and the credentials we have to provide. This example, I'm using a local stack a backend to store the data, but if you have an S3 bucket somewhere, it should actually be easier. So this is the declarative way we define sources in Dashtool. And now that we want to proceed, we add this file to our main branch and we run Dashtool build, which will then create the according tables in our object storage. The Dashtool workflow command will then create the Argo workflow according to that, so that it can update or refresh the data in the Iceberg table. We can then run the Dashtool apply command, which will apply this workflow to the Kubernetes cluster. We will then switch over to the Argo console, where we can see our newly created workflow. We can then start this workflow, and Argo will download the according Docker images and executes the command. Once it's finished, the data is available. We can check that by, or I check this here by using a Frostbow query engine, which is data fusion distribution with support for Iceberg. And I'm selecting here from our purchases table, which is from this Faker data set, and see if we have any entries. And as we can see, the data has been loaded correctly into our object storage. Another thing to mention here is that that I'm using a file system tables for Iceberg, which means I don't require any external catalog. Typically with Iceberg, you require external catalogs that store the namespace and table information. With the file system catalog, this information is just taken from object storage, and you don't need an external catalog, which makes it also easy for testing purposes. For production environment, where you might want to have role level security or like role-based access controls, a proper catalog can be better. So after we've loaded the data successfully into our object storage, we would then like to create additional transformations. And as I said, in the development process, now that I have the data loaded into, I would first like to try out and see what data I actually want and if my queries are actually running correctly. That's why I'm creating here another branch, which I'll call Silver, where I can test out the data transformations. Then I'm gonna create here a file where I'm just using a different naming conventions for my files and maybe restructuring the original data into maybe a dimensional modeling or something, or I also clean out some unwanted features. Additionally, I also create another dimension table where I'm going to do the same. But actually here I'm not doing a lot of transformations. I'm mostly just cleaning the data and putting it into the form that I actually want. We will then add these files here on the left to the Silver branch in our development environment. And to apply this also to our object storage, we will again run Dashtool build, Dashtool workflow, and Dashtool apply to first create the entities, then create the Argo workflow and apply the workflow to the cluster. We can then head back to the Argo console where we are executing the workflow, and we can see that the transformation is successfully executed. For now, this data just lives on the bronze branch and hasn't been merged on the main branch. But we can see that the transformations are being executed correctly, so we can head back to our development environment and merge the Silver branch into our main branch. You can see this here at the top, that I'm merging the Silver branch into the main branch. After that, now the Silver branch has been merged into the main branch in our development environment, but we haven't applied anything to the object storage. There, these newly created tables are still on the Silver branch. We have to run Dashtool build here again to also apply these changes on object storage, so that the Silver branch in our Iceberg tables are also merged into the main branch. Now we can have a look if the data arrived in our silver layer, and we can see that it was successfully loaded. And now that we have cleaned data sets, we can continue by creating a gold branch where we can also test out new queries we'd like to run to answer certain questions we might have. For example, we might be interested in the monthly sales that we've collected. Therefore, we created the gold branch, and we will create a monthly sales SQL files on that gold branch to perform the actual query. You can see the query here, which sums over the prices of the products and groups them by month. We will then again add this monthly sales files to the gold branch, and just like before, we will run Dashtool build to actually create the new entities or the new materialized views on object storage, and then Dashtool workflow and Dashtool apply to create the workflow and apply to the Kubernetes cluster. Again, we will switch back to the Argo workflow console, execute the workflow, and see that it finishes correctly. Just as before, we will merge the gold branch into the main branch. Then again have to run Dashtool build again to also apply the merging on the Iceberg tables. And then we can also run our select clause to see that the newly data has been computed in the materialized view. That's it. Thank you very much for listening. And if you have any questions, feel free to ask.
Thank you, Jan. That was great. One question so far. How dependent is Dashtool on Argo, and is Argo and Kubernetes a requirement for using Dashtool?
So far, it's so you can create the materialized views independently of Argo, and you can then go ahead and call a refresh function on these materialized view by yourself. You don't have to use Argo for that. So far, I've implemented Argo to trigger these refresh operations for the materialized views because it's easier, or for me, it was easier than using Airflow, for example, because these are actually just very simple Docker containers that need to run, and you don't need so much scheduling on top of that. But I'm thinking about it. It always depends on the use case. Like if there's a need for it, I was also thinking about using different orchestrators. The thing is that often these other orchestrators are then also executed. They must be executed somewhere. And nowadays, the somewhere is often Kubernetes. If you run Airflow on Kubernetes, you can actually also just run Argo on Kubernetes, because I think it's just much easier to set up.
Are there any frameworks for running Dashtool with Airflow or Dagster for orchestration?
Well, so far I haven't looked into it, but since these Docker containers are actually like idempotent operations, so you could just do a cron job which like periodically starts all these Docker containers, and if there's no work to do, they will also they're not like, if a materialized view is fresh, the Docker container will check that, and it will not rerun the entire query. So you could actually just make these refresh calls, and if there's nothing to do, actually nothing will be executed. And so the orchestration with other orchestrators should be quite simple, because it actually it doesn't matter so much in which order they execute, because they're not doing anything if there's nothing to do. But I haven't implemented anything for Dagster or Airflow so far. So thanks again for having me. was really cool to talk about my my work. And
yeah, thank you so much for joining us. And we'll have the next session on December 11th. Folks, you can sign up on LinkedIn or at osacom.io. And thanks, Jan, so much for kicking off this this series.
All right, thanks.